one other concept I'd like to introduce related to buffers, and this is found on page 184. I have here 3 different beakers, all of the same buffer system. You can see that actually they all have the same pH. And perhaps that shouldn't surprise you because you have equal concentrations of both the conjugate acid, conjugate base. And it's the same buffer system, so the pH is going to equal to pKa. But those buffers aren't all the same. Remember that part of the definition of a buffer is a solution that can resist the change in pH upon the addition of strong acid, strong base. So perhaps to see that you can actually hear me, which of these buffer systems do you think would be a better buffer? Which one would be better at resisting a change in pH? Would it be buffer A? Would it be buffer B? Or would it be buffer C? You can see that there's something about the concentration, right? And maybe that's just kind of intuitive, that if you've got more of the buffer component, that's going to be helpful. Now, we say that a buffer resists a change in pH. Well, it's not because a buffer has some kind of magical properties. It's like, okay, add some strong acid and poof, somehow the buffer is able to resist the change in pH upon the addition of strong acid. The buffer is actually doing something. And so here we're talking about the buffer capacity, and it's defined as the amount of strong acid or base that can be added before the pH changes significantly. What I'd like you to be thinking about here is, let us say that I'm going to add some strong acid to all of these different buffer systems. So and I realize that I haven't given you a whole lot of space here. Maybe in future course packs, I'd give you a little bit more space, but I'm not going to write a whole lot. And I'm kind of addressing the key question number 7. Which of the above buffer systems has the greatest buffer capacity? What property of the buffer system can determines its capacity? Well, we've already indicated concentration, but let's see how or why. And as I say, hopefully you can squeeze this in. What I'd like you to be considering here is strong acid. So let's say we add some strong acid. Now that could be in the form of hydrochloric acid, nitric acid, perchloric acid. But of course, when you add strong acid, essentially what you're doing is you're adding hydronium ion. Okay. So as I say, a buffer doesn't resist a change in pH by magic. It's because there's something in the buffer that's going to react with that hydronium ion. Now, if you were just to add hydronium ion to water, well then, the thing is that the pH of that water is going to be automatically lowered because we're automatically increasing the hydronium ion concentration. Now, of course, it depends on how much water you add it to, but the pH is just going to drop if you add hydronium ion to neutral, pure water. Whereas if we add hydronium ion to a buffer system, there's something in the buffer that can react with that hydronium ion. So I'd like you to be thinking, what about in this buffer system? What's going to react with this hydronium ion? Will it be our conjugate acid, which we can represent as HA, or will it be our conjugate base? And hopefully this is kind of intuitive, but maybe you can give me some feedback. What is the hydronium ion going to react with? So that's the whole point. Now, this is why a buffer system needs both conjugate acid and conjugate base, because it needs to be prepared, if you will, to resist the change in pH upon the addition of either a strong acid or strong base. So if you've got the conjugate base, well, it can react with the strong acid. Now, what are the products going to be of this? Well, in a sense, this is just kind of like a titration reaction. And so what happens here, of course, is we form H2O. The hydronium ion donates its proton to the A negative, and we form HA. So a buffer system has got that conjugate base, the A negative, and in a sense, it sort of soaks up the hydronium ion by producing some more weak acid. So can you see that essentially we added some strong acid, and I'm going to do some labeling like this, that the buffer is going to take that strong acid and convert it to some weak acid. And what's going to happen to the ratio of our conjugate acid, conjugate base in the buffer is, yeah, the weak acid's concentration is going to go up a little bit in using up some of the hydronium ion. Alternatively, let us say that what we do to our buffer system is we add some strong base. So, of course, we can represent that by just adding hydroxide. Hopefully, it's no surprise to you that what that strong base is going to react with is our weak acid in the buffer system. That will produce correspondingly H2O plus A negative. Again, a similar sort of thing, that our strong base effectively gets converted into a weak base. Now, you can do some stoichiometry associated with this. You can calculate, you're added so many moles of strong acid and so many moles of strong base. You can imagine that a buffer would have a greater capacity if there are more moles of conjugate acid, conjugate base within a given volume. The more moles of conjugate acid and conjugate base within a given volume means more concentrated solution. So the idea here is more concentrated, or how about we write it like this? The greater the concentration of HA and greater the concentration of A negative equals greater buffer capacity. Because there's more of these components to react with the strong acid and strong base. So it's really this 1 molar buffer system that would have the greatest capacity. The pH in both cases would start off the same, but it would take less strong acid or less strong base to use up those buffer components in our buffer C. So I'm hoping that this concept is fairly straightforward. Again, to have a buffer, you need both substantial amounts of conjugate acid, conjugate base within a 1-to-10 ratio. If you have a more concentrated form of these guys, then you're going to have a higher buffer capacity. There's more of the buffer components to react with the addition of strong acid, strong base.